Hello, and welcome to Quantum Computing Principles with Music. In this video, I'm going to illustrate some fundamental principles on which quantum computing is built, as they could be applied to music. Imagine this scenario. A computer produces a sequence of ones and zeros. We use these outputted ones and zeros to determine which note to play, choosing between two songs. For example, if all ones are outputted, then it plays all blue notes. Mary Had a Little Lamb. If all zeros are outputted, then it plays all yellow notes. Twinkle, Twinkle, Little Star. If a combination of ones and zeros are outputted, then some notes from each song are played in the order corresponding with the ones and zeros. With a classical computer, if you decided what operations you wanted to use for this process, as long as you started with the same numbers and performed those same operations, it would always produce the same output. Not so in quantum computing. Let's explore 4 quantum computing concepts through this analogy. The first concept is superposition. In a single quantum bit, at any one time, both values of 1 and 0 can be stored in a single bit. When the answer is read, there is some probability of reading the 1 or 0 state. In our musical example, we are imagining that we have 7 different qubits. Each qubit controls a single note that will be played. You can see that I've labeled these 7 qubits and associated them with each note that's playing. Right now, as it begins, there is a 50-50 probability of reading a 0 or 1 each time, which will correspond to playing a blue or yellow note. So now I'm going to turn on tracing, and it's going to take a record of what happens each time. If we rerun the computation, notice that when we measure it again, we get different results. So those 3 runs were different, even though the state of the qubits were all the same for every run, which was 50-50 chance in each one. Now the second concept we'll look at is about measurement. Measurement itself collapses this superposition, meaning that any subsequent measurements will always result in the same answer unless we rerun the computation. Therefore, if we keep measuring the same bits without rerunning the computation, we will get the same values. The third concept is that quantum computations manipulate these probabilities. It's not that useful to have a bunch of bits that have a 50-50 probability of being a 1 or a 0. We might as well just flip coins. In order to do useful computation, we don't want that 50% probability at each bit. Instead, we manipulate those probabilities through quantum operations. This is depicted here by the size of the note. If I click on a yellow note, it gets bigger and the corresponding blue one gets smaller. As that yellow one gets larger, it indicates a growing probability of reading out yellow and a shrinking probability of reading out blue. The last concept is entanglement. Operating on everything as on the bit level is not very powerful. Think of addition of 2 numbers as if those 2 numbers were stored in binary, just as ones and zeros. Or think of it in base 10 as we already understand. If you add 1 to the number 499, That's a very different thing from adding 1 to 490. The hundreds place is affected by the values in the tens and the ones place. Not a perfect explanation, but entanglement allows you to manipulate the joint probability of a sequence of bits instead of viewing them as completely independent bits. In our case, we will look at the probability of all ones or all zeros. In reality, there are also other possibilities, but we will simplify it for this example. So I'm going to entangle it now. And now, when I try to increase the probability of blues, it doesn't just affect the one qubit, it affects all qubits because I've already used entanglement to restrict the outcome to either all ones or all zeros. So the probability is the same within all qubits. Also, once I measure the first qubit, you can see that it's known what's going to be happening for the rest of the qubits. Even without measuring all of the rest of the qubits, I know that if I get a yellow for the first one, that means I must have a yellow for all of the rest. And so, even if we rerun it, we can get all yellows or all blues, but we can't get anything else. So hopefully you learned 4 crucial principles for quantum computing. First, instead of holding either a 1 or a 0, they hold a superposition of 2 states. At the time of measurement, there is a probability of reading out a state of 1 or 0. The quantum operations manipulate those probabilities. Once measured, however, the state is collapsed and the measurement will always be the same unless the computation is rerun. Finally, entanglement means that instead of just looking independently at the probability of a single bit being a 1 or a 0, you can perform quantum operations that manipulate the probability of combinations of several bits, allowing some combinations but not others.